Good morning, ladies and gentlemen, and thanks, Paco, for your kind introduction. I'm very pleased to be here. It's an honor to be speaking to you today, and I speak to you as the CEO of the International Water Association. What I'd like to talk to you really about are some of the challenges that we see within the water sector internationally and how we are trying to respond to some of those challenges. When I look around the world, I think that what you see is that in most countries we are still promoting a sort of a 19th century approach to water infrastructure, particularly in the urban space. Most of our systems were thought of when we thought that water was abundant, when the environment was benign and populations were relatively small. And so we built these systems where we move water long distances. A lot of energy is expended because water is quite heavy. We treat that water to a single quality, and we use it for all purposes. And in some cases, we treat that water before we discharge it, but in many cases, we don't. But it's this idea of having one quality for everything and using the water only once. And we've promoted this approach to most countries as an all-or-nothing proposition. And in many countries around the world, frankly, this is not affordable. And with global change pressures affecting populations, urbanization is moving very fast, particularly in the developing world, and then climate change, which is affecting our water availability. The supply-demand deficit is going to get worse as we move forward, and so these sorts of systems are probably not going to be appropriate in order to respond to some of those challenges. I think the biggest challenge that we face globally is wastewater. 85% of wastewater is not treated, and it's not just the usual suspects, South Asia, Sub-Saharan Africa, but you find parts of Europe, parts of Central Asia, and also South America, where large parts of wastewater is not treated. And I think, for me, coming from the water sector and moving around, I feel that the next 20 years will really be the golden age in terms of wastewater provision. And you see, in many countries, huge investments in China, in India, and in parts of Africa and South America, a lot of emphasis now on wastewater. So I think that's really where the attention will be in the next 20 years. But we have put wastewater systems all over the world, and this is a diagram from some work that we did in my last organization at EME. We have built lots of wastewater treatment systems, but we haven't engineered them particularly well. We haven't thought about some of the challenges locally in terms of operational maintenance. So if you look at this diagram, this shows you the number of wastewater treatment plants in Ghana, but these are actually the number that are working. So we built lots of wastewater treatment systems, but the majority of them become dysfunctional. They don't work. And so I think the challenge for us all now is to rethink how we engineer these systems so that they're appropriate and that they understand the local context in which they operate. I think for the developing world, as I said, the next 20 years will be a golden era in terms of wastewater. And if you think about the last 40 to 50 years in the West, it's almost been like a pilot study when we think about wastewater. We started with fairly clunky, not so efficient wastewater treatment systems, which we experimented with, we tested, and now we're starting to evolve technologies that are allowing us to have much smaller footprint systems, systems which are much more energy efficient, and systems which, allow us to recover some of the resources from our waste streams. And you see a lot of the changes that have taken place in terms of innovation has been around adjusting the physics of the process, changing the settling characteristics, for example, granular sludge, or changing the viscosity of our sludge, like with thermohydrolysis. These types of changes allows us to intensify our activity in terms of our treatment and get greater efficiencies at a lower energy cost. So it's sort of doing more in less with less. And with advanced control systems, with sensors and automation, we're able to sort of optimize stoichiometric, the pressure, the flows within these systems. That gives us maximum efficiency. So I think for the developing world to learn from the West and really start to deploy some of these more innovative approaches is really the way forward. When I think about the water sector, I see a big change in perspective, and the biggest change that you see is in this idea of what it is we want the water to do for us, the productive use. So what is it we want the water to do for us, and how do we create a quality and quantity for that particular use? So if we want to drink water, we need a certain quantity and quality. If I want to flush my toilet, the question is, do I need water? And if I do, what type of quality would be appropriate? And you see a big change in the water sector where we're starting to now create different grades of water for different uses. So on the left-hand side, you have the West Basin Initiative from California, Los Angeles, where they create what they call designer waters. They use innovative membrane technologies. They take the wastewater from the city, and then for different types of industries, they create different grades of water. So it's not one grade, but a designer suite of water. On the right, you see wastewater being productively used to dilute saline water, seawater, so it brings down the cost of desalination while at the same time treating the wastewater. So we're starting to recognize that all water is good water, but it's just water of different grades. And how can we use that water effectively? And critical to this sort of productive use thinking is viewing the whole water cycle as one, and recognizing that all waters that flow within that water cycle are good water, and the trick is to manage your need for water with these different types of water. So if I need more drinking water, then should I extract more surface water and groundwater, or should I reduce my leakage? Or demand management? If I want to have water for gardening, can I use my grey water and black water? So this sort of systems view of the water cycle is how we're moving. But the challenge we find is that institutions are fragmented. And so you don't get good cohesion between the people responsible for drinking water with those people responsible for wastewater, the people running the networks on one side with the people running the networks on the other side. So that becomes a little bit of the challenge. But critical to this is really modeling, a systems approach to modeling. And this is where you're modeling flows and contaminant fluxes so that you can match the different quantities of water for different uses. And so you can do a sort of water balancing, so you can reduce the overall water footprint. And some people in IWA, they're starting to model sort of water as a packet moving through the water cycle. And that packet has a signature. That signature quantifies or captures the amount of energy that was expended in producing that water, the chemicals that were used in expending that water. And by having these digital ledgers and watching water move like packets, you can start to do this type of water balancing. This is some work we did a long time ago in Africa, where in Nairobi, where the response of the government was really to meet the growing demand just to extract more surface water, right, and groundwater. So they wanted to build more infrastructure to meet the growing demand. But when we start applying these sort of systems-based models, we start seeing that actually there's quite a lot of water embedded in the system that can meet that growing demand. And so you don't really need to invest in new infrastructure. And you can start playing with options where you do more exotic types of treatment. And sometimes it might be more expensive, but in many cases it could be cheaper. And we've published a book on this. So this idea of modeling water as packets as they move through the system is also quite useful in the way in which we manage, for example, leakage. Because we tend to think of water, once it's in the distribution system, as being of an equal cost. It's an average cost. But actually, different parts of the system, the water is costing a different amount. The energy used to produce that water, the chemicals used to produce that water, if it's coming from different sources. And so by using these types of digital ledgers, we can start to target where we put our investments into things like pipe rehabilitation, leakage reduction, where we get the biggest bang for our buck, because we start to recognize that not all the water is of equal cost. Some water has cost us more to produce. And also this idea of having these digital ledgers allows us to also support decentralized systems. You're finding many systems that are coming off the grid, and they have some localized storage, and they're able to negotiate with the main supplier at what time they want to withdraw water, because the water costs a different amount at different times of the day because of the energy, etc. So they can start to negotiate and engage in smart contracts, using things like blockchain in order to buy water when they need it. The other major shift that you see in the water sector is the way in which we view wastes, and I think all of you know about this. But again, having a sort of a systems perspective of your water cycle allows you to look at where in the water cycle you want to try and capture some of these resources. So, for example, energy can be captured in the drinking water cycle, where you have areas of high pressure. The energy is quite limited, but you can capture some of it. In your collection systems, of course, you can get heat using heat exchangers, but also if elevation works in your favor, you can generate some hydro energy as well using turbines. And then at your wastewater treatment works, the classical sort of biogas or biofuels or microbial fuel cells. So there's lots of places where there's a potential to capture energy and move towards energy neutrality or even a net positive energy. And similarly with nutrient recovery, you can recover nutrients from a decentralized sort of fecal sludge management approach where you have septic tanks, but equally you can capture your nutrients from the centralized wastewater treatment works, precipitating out the phosphorus. But the big problem for me in this space of resource recovery and reuse is not the technology. I think the technology is evolving and it's creating lots of opportunities, but it's the fact that engineers fail to understand the business models that will sustain this type of resource recovery operation. Very often it's engineers telling you that we can generate so many tons of fertilizer, we can generate so much quantity of energy, but they don't understand who will be the customers for these products that they generate. So if it's fertilizers, is it farmers, is it a fertilizing company? And then they don't really appreciate what the value proposition is of their fertilizer. Is their fertilizer cheaper? Is it more effective? Is it greener? Why would somebody choose to buy their fertilizer over somebody else's? And then the cost to move that value proposition to the customer is not fully understood. And so what we find is that these systems fail because we fail to understand the business models that are going to make them financially viable. This is the classic example of struvite it's implemented in Chicago in the Stinkley plant, one of the largest wastewater treatment plants in the world, where they precipitate out phosphorus and they create this crystal struvite. And most people, they think when they analyze this that really the money is coming from the sale of the fertilizers. But actually very little of that money is coming from the sale of the fertilizers. Most of it is coming from the fact that they are managing the nutrient issues of that wastewater utility. And at the same time, they are also reducing the maintenance costs for that utility because they are reducing pipe blockages within their return activated sludge lines. So those are the two major income streams that make this thing sustainable. Financially viable, and of course they make some money from the sale of the fertilizers, but it's very context specific, and I think we need to start thinking about these things a bit more. The last thing I wanted to touch upon is really the challenge around innovation. The water sector is viewed generally as being quite conservative, and it's for rational reasons. We are very risk averse in relation to public health. We have very tight budgets. And so we spend money very carefully, and the upfront cost associated with innovation makes it sometimes very difficult to procure. But I think that, when you look at the water sector, you can see that, this is a slide which talks about a particular process, right? This is thermohydrolysis, can be. The paper, I think, was written in 1978, the original paper. And it wasn't until about 2007, 2008 that this technology actually started to deploy. So it took about 30 years from when the paper was published to when actually the technology started to deploy. So there's a really big lag time between people having ideas and when those ideas get implemented. And I think it's important that as a sector we accelerate that. I think one of the problems that we face is we think of our sector as being as homogeneous. We think that everything within the water sector are elephants. So elephants have very long gestation periods. They carry their child for a long time. So the R&D process for elephants is very long. And then they have very long lifespans. And we tend to think of the water sector because we have these large concrete infrastructure that everything is an elephant. And so we think that nothing changes. But actually the water sector also has horses. And these are the mixing devices, the pumps, which have slightly shorter gestation periods and much shorter lifespans. These devices are what improve the physics of your processes, the settling characteristics, the viscosity. These can be used to optimize your elephants much more effectively. And then, of course, you have hairs, your sensors, your controllers, which have very short gestation periods. They mutate, so they change very rapidly. And so their lifespans are very short. And I think we need to recognize that the water sector is not just elephants, but there are these different components, and each of these components have their own independent sort of innovation cycle. But unfortunately, we tend to manage everything in one way as elephants. So we procure our horses and our hares as if they were elephants. And it benefits those people that sell those technologies to the water sector. This is an example from Washington, D.C. A colleague of mine, Vairavamoorthy, was working there, and you can see here they employed horses and hares to improve the performance of their elephants. They had large grey infrastructure systems, but by employing, for example, the Canby process, they could almost double the loading of solids in their digesters. They could intensify their processes, and with the hares, they could control the chemistry within those reactors, the flows, and they could also have alarms which trigger when there are digester upsets to minimize that. So you see the opportunity here to sort of deploy your hares and horses in a way that you can really repurpose your elephants. And this is something that we as a sector have to start thinking along those lines. And I think when you think about the water sector, we tend to verticalize our technologies, right? So the hares, the horses, and the elephants are viewed as one continuum. And I think the challenge for us moving forward is to try and unbundle these different aspects of our water sector. So the people that we employ to manage the hares are people who really understand sensors. They understand these devices. They go outside the water sector to procure some of these devices from other sectors that are innovating in this space. Similarly with the horses, you know, the mechanical devices that they buy, they can purchase them from other sectors. But they understand that these devices will only last a certain period, and they are always preparing for the next turnaround in terms of that innovation. And it allows us to really then repurpose the elephants that we have. The one thing that I would say is that with these emerging economies around the world who are implementing wastewater treatment systems, I think we should encourage them to avoid investing in elephants. I think they should move away from these very large, fixed concrete infrastructure that lasts for 50 years and think much more around sort of smaller footprint package type plants that also have shorter gestation periods and have, you know, much sort of faster innovation cycles. And I think that's the way forward. So to conclude, I will say that the water sector is currently facing quite a lot of challenges. And I don't think that we are in a position to stay in the business as usual lane, because with global change pressures and the demand, the supply-demand deficits that we're going to be facing in the future, the way we currently run our systems is not going to enable us to manage our water effectively. What we're currently doing is we're in the middle lane. We're trying harder, okay? We're trying to optimize our systems as much as we can. But I think really what we need to do is to transition much more to a sort of more circular economy approach where we try to use water as many times as possible. We try to create different grades of water for different uses, and we try to capture as many of the resources from those waste streams as we can. And we think about all of these things from the design stage itself. So where we locate the plant, the types of technology we use is really to facilitate that. It's not something that we retrofit. So that concludes my presentation to you. Thank you very much.